Good morning. Today we're going to work on section 9.2. This is called goodness of fit, and that is the objective for the day. So when we run our chi-square test of inference, what we're doing is looking at two categorical data pieces, and we're looking at the distribution for those populations. And remember, you can use any number of populations here to make a comparison. When we run the chi-square goodness of fit test, we're still looking at a categorical variable, but we're only looking at one sample with k possible outcomes. We're going to use a bag of M&Ms to go through this example. So the bag would be one sample, and the k possible outcomes would be the different color M&Ms in the bag. We're going to create a one-way table. So we're going to summarize what we see from the bag, how many red we observe, how many orange we observe, and so on. When you write up the null hypothesis, you're going to list all the probabilities for each of the different events. So the null says that we have proportion number one, whatever you specify it to be, and it equals, and you're going to fill in the blank with the proportion stated in the problem. And you're going to do that for group 2, and so on until you get to the final group, P sub k. The alternative hypothesis says that at least one of the proportions that you've listed is different than claimed. We're not trying to disprove all of them, just that one is different. So just like the chi-square test, we're going to find the expected count for each category, and for us that will be each different color M&M. And the way to do that is to multiply n, our sample size, times the probability for each specific event. We'll calculate the chi-square statistic the same exact way we've done when we've had an R by C table. So it'll still be observed minus expected squared all over the expected count. We're still going to use degrees of freedom. In this case, it's k minus 1. So if there were 10 different colors of M&Ms in the bag, we would do 10 minus 1. And we want all of our expected counts to be at least 5 or more. And remember, the chi-square test statistic is one-sided. We're looking at how far into the right-hand tail our value actually is. So we'll go through our example. It says Mars Inc. makes M&M milk chocolate candies. Here's what the company's consumer affairs department says about the color distribution of its M&M's candies. On average, the new mix of colors of M&M's milk chocolate candies will contain 13% of browns and reds, 14% yellow, 16% green, 20% orange, and 24% blue. So we want to test if that's really accurate when you grab a bag of M&Ms at the store. So a bag of M&Ms was selected, and they counted each color, and this is what they found. There's also 60 M&Ms in the bag. So we're going to write our null hypothesis. According to the company, they claim that there's 24% blue, 20% orange, 16% green, 14% yellow, and 13% of both reds and browns. So we list them all separately. We want to make sure we include everyone. And then our null hypothesis says that we believe at least one of those proportions is different than they claim. Remember, you can stop the video at any time if you want to calculate any of the examples on your own and then check. We're going to start with our expected count for orange. Remember, n is our sample size, and there were 60 in the bag, and the probability of orange was 20%. So that means we expect to see 12 orange M&Ms. We're going to move on to green. There were 60 M&Ms in the bag. They said 16%. We expect to see 9.6. Now remember, this is a calculated value. We know we're not going to see a half of a green M&M. 14% yellow, so we expect to see 8.4. 13% red, 7.8. 24% are blue, so we expect to see 14.4 blue M&Ms. And then 13% are brown, so 7.8. So this is a summary of what we've observed and what we've expected. We're going to go through and use our chi-square formula to calculate our statistic. So I started with blue. Remember, it's observed minus expected squared all over expected. And I did color code each of the pieces to match the M&M color. And remember, you can pause it so that you can calculate the decimal equivalents on your own. So moving along to our decimal equivalents for each of the colors, and again, they're color coded. So remember, the bigger the decimal value, the more it's contributing to that chi-square value. And I have chi-square at 8.03173. So is this large enough to show us that the proportions could be different than claimed? So we're going to go to our calculator. Remember, we do have degrees of freedom, and that needs to be calculated before we move on. So there should be 6 different colors of M&Ms in the bag. So we want to do 6 minus 1, which gives us 5 degrees of freedom. So on your iPad, we're going to find that x squared or chi-squared CDF. Remember, 0 is our lower bound, our statistic is the upper bound, and then 5 degrees of freedom. And then because we're in the upper tail, it'll be a 1 minus. So we didn't talk about alpha, but typically it's at 0.05. So for this example, there is not significant evidence. And we'll write up our conclusion to say that at alpha equaling 0.05, that the proportions do not seem to be different than claimed. Keep in mind that was 1 bag of M&Ms. If I grab a second bag of M&Ms, the proportions could be different. Maybe we would meet the criteria to reject the null, and again, maybe we wouldn't. But in the factory every day, the percentages is what they create in their factory, and then they're broken up into bags kind of randomly, so it's highly unlikely that any bag would contain the percentages that they claim. These are the 2 problems that you're going to work through. If you have any questions while you're going through the problems, you can call me at home, you can shoot me a text or send me an email, and I can help you work through that problem. Some of you have been sending me texts and asking me if it looks good. You're welcome to keep doing that. And other than that, have a great day.